Today's section 5.4, the multiplication principle. Okay, so suppose we want to travel from one point A to another point C, and we need to stop at a point B in between. Okay. And now we suppose that there's not just one way from A to B, but actually 5 ways from A to B. And not just one way from B to C, we have 3 ways from B to C, right? So we could take path 1, path 2, path 3, path 4, or path 5, or we take path alpha, beta, gamma. And now we ask the question, how many different paths are there from A to B? Okay. And this will become important when we start talking about things like probability and stuff like that, and you'll see, okay, there's some real-world reasons why we'd be interested in such a question. Okay, so let me highlight 1 or 2 of these paths in case you're a little confused about what I mean. I could take path 2, and then I could take path gamma, right? So one possibility is 2 gamma. Or otherwise, I could take path 3 and then path alpha. We could call that 3 alpha. And the question is, how do we quickly count all of the different paths that we can take? Well, one way we could do this is with something called a tree diagram. We'll have one node being A, and then 5 nodes coming off of A, which would represent the 5 different paths we could take from A to B. Then, from the end of each of these nodes, we could have a total of 3 different paths, alpha, beta, or gamma. And this quickly becomes boring, but I may as well finish what I've started. Okay, so now the end of each of these nodes on this tree, it's called a tree because there's no loops in this drawing. Just like a tree doesn't loop, it just goes outwards. Now I can count all those different nodes at the final stage, and each of those nodes is a different path. For instance, the path 2 gamma that we found before, we can find it in this tree too, 2 gamma. Or 3 alpha that we took before, that's right here. Right? So this diagram has encoded all of the possible paths. And now we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 total paths. Now, obviously, we don't want to have to draw a tree like this every time we would do a problem like this. For one, it's not that much fun to do. And for 2, once you have more than 2 choices, these trees are going to be extremely large. They're going to have so many nodes, okay? So this is where the multiplication principle comes in that this section is named after. And I'm going to write this down. This is the multiplication principle. It says the following. Suppose a task is composed of consecutive choices. The total ways this task can occur is the product of the number of options of each choice. Okay, so the total number of paths is the product of the number of choices we have for the paths, right? So for our choice 1, the first choice we had 5 options. Choice 2, above when we talked about the paths, we had 3 options. So the total possible options is 5 times 3, which is 15, which is what we just counted. Right? Okay, so now we're going to do a few more examples like this, and we'll introduce some notation at the end. But let's do some more examples using this multiplication principle. A corporation has a board of directors of 10 members. The board must select from them a chairperson, vice chairperson, and a secretary. How many ways can this be done? Okay, so the question is, how many choices do we have for the president of, for the chairperson of this board? How many are live options? 10. Thanks, Jake. So the first choice for chairperson, we have 10 choices. How about the second choice? How many do we have to choose the vice chairperson? It's not 10, right? Because we can't have the chairperson and the vice chairperson be the same person, right? So now we only have 9 choices. So choice 2 is going to be 9. And then finally, when we're choosing the secretary, we have 8 choices because we've already chosen a chairperson and a vice chairperson. So I have 3 choices. I have 10 for the first choice, 9 for the second choice, 8 for the third choice, and that product is 720. So there are 720 combinations of chairperson, vice chairperson, and secretary that are possible on this board of directors of 10 people. Questions? Does that make sense? Okay, let's do another example. How many ways can a 9-member baseball team arrange itself in a photo? Okay, we're going to assume they're all in a line, right? So we've got 10 baseball players. How many different ways could they arrange themselves for a team photo? Well, how many choices do you have for the first person on the left of the photo? You have 9. Now, for the second person, you only have 8 remaining, right? So it's 8 for choice 2. Choice 3, you have 7. Choice 4, you have 6. Choice 5, you have 5. Choice 4, you have, or choice 6, you have 4. Choice 7, you have 3. Choice 8, you have 2. And choice 9, you have no choice. There's the one person remaining, right? So we'd have to take 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and I've done that for us, thankfully. This is 362,880. So there's 362,880 possible arrangements for the team photo. Why anyone would care about that is anyone's guess, right? Okay, now, writing this out wasn't that bad of a chore, but sometimes in math, notation can help us express things more compactly, and that's what I'm going to talk about now, the notation for factorial. So definition. If n is a positive integer, the number n factorial is defined to be, and we write it n exclamation point, that's the notation for factorial, and it is n times n minus 1 times n minus 2 all the way to times 2 to times 1. Okay, so that's what n factorial is. And so the previous problem, this was just 9 factorial, right? So that's, instead of having to write 9 times 8 times 7 times 6 times 5, okay, we just write 9 factorial. And that just makes it a little quicker to write something down. Now, of course, when we learn about permutations and combinations, which I assume you might have seen before, you remember these, have we seen this, permutations and combinations? Yeah, and if you remember, there were factorial formulas for these, right? So we're going to be getting to that soon, and so we have to develop or remind you about the factorial notation. Okay, and yes, so we'll be using that a good deal in the future. Okay, one more example, and then I'll assign the homework. A license plate uses 3 letters and 3 digits. How many plates are possible? Okay, so we're using 3 letters. There's 26 letters. So we get 26 choices for the first letter, and we still get 26 choices for the second letter. There's no rule that you can't have a letter repeated. So we still have 26 choices for the second letter, and then the third letter, we still have 26 choices. Now we've chosen our 3 letters, now we choose our 3 digits. And there are 10 digits, 0 through 9. So for the first digit, we have 10 choices, second digit, 10 choices, third digit, 10 choices. This, when we multiply it out, is 17,576,000. Okay, so I'm just going to assign the homework instead of any in-class problems because we have a lot of time today, so you may as well just use it to get started on the homework. You'll have time to get deep enough that if you get stuck, you'll be able to ask questions. So the homework is going to be 8 to 48 even in section 5.4 that we're in now. All right.